All right, guys. So we are in Matlab now, and we will try to construct our example system here, and we will try to design an LQR controller for it. Okay, so remember that the system that we have solved was actually the A matrix was given by 0, 1, 0, 0. Okay, so I will try to also show these matrices for you. B was equal to 0 and 1. It's a column matrix, right? And let's say that our system's output, in fact, we will observe all the states. So this is not very important, but we can select our first state as our output of the system. Sorry about that. That's not correct. We should have C is equal to 1, 0, and D is equal to 0. Okay, so let's construct our system. System equals state space, the matrices A, B, C, and D. Okay. So Matlab responds by showing us what the system is, the A, B, C, and D matrices. Right? So let's also specify an initial condition. Let's say that x0 is the first state, the position starts at 10, and the second state, which is the velocity, starts at 0. So this is our initial state. Now we can obviously show the initial state response of the system. This is given by the initial command. Okay, so if you take a look at the initial command, you give it a system and an initial condition, and it's gonna construct the evolution of the state. Okay, so for example, this system, remember, it's a mass driven by a force. So if the input is 0, but you have an initial state at a certain position, the system will not have the states will remain at their values because nothing's going to happen without any force. So the position will stay the same, the velocity will stay at 0. Okay. Obviously, if the initial state was with an initial velocity, the position would be increasing or decreasing at a constant rate. Now, so we have our system. Now let us try to construct our LQR. Okay. In order to construct the LQR, we need to specify the Q matrix. Let's say that we only care about the first state. That means we want to take the position to 0 as fast as possible. So Q is composed of 1, 0 and 0, 0. That means we don't care about the velocity. We don't have any bounds or any constraints on the velocity. And since we have a single input, we can just set R is equal to 1 as a scalar. Okay. And there is also another design parameter for the LQR function, but this one is not important for us. It corresponds to a cross term between the state and the input. So you can take a look at it, or we can take a look at it in a minute. So we will take this as 0 and 0. Okay, so if we look at the LQR function that we will use, and let me go to the top. Okay, so you see that J is equal to integral x prime qx u prime ru and 2 times x prime n u. So this is this term that we are taking as 0. So for the time being, we don't care about this term. Okay, so we have q, r, and n, the design parameters of the LQR. So we will design the LQR by having our return values. You see these return values at the top are specified here. So this will calculate the optimal gain matrix K. Okay, it's gonna also give us let's see what else is being returned. So hold on, such that so the input is the linear state feedback UKX minimizes the cost function given by J subject to system dynamics that we are specifying. Also returned are the solution S of the associated algebraic Riccati equation and the closed loop eigenvalues of the resulting system. Okay, so let's make that calculation. So KSE is equal to LQR, the system that we have defined, Q, R, and N, the design parameter of the LQR system. Okay. Now, the K, the optimal feedback matrix, is given by 1 and 141. If you remember our solution, in fact, our K matrix was 1 and square root of 2. So if we calculate square root of 2, we would see that this corresponds to what we have here. So we have obtained exactly the same K as our solution. Okay. Let me see also the solution of the algebraic Riccati equation was given by the P matrix. So let's see whether that is given to us as well. So this is the S matrix. If you compare the S matrix with our calculation as P star, there is a correspondence of this. So this S is actually our P star. So that is also verified. Now let us calculate A bar, which is our new closed form, the closed loop state feedback system matrix, B times A minus B times K is the new matrix. And if we actually take a look at the eigenvalues of this matrix, this will be our new system poles. And if you take a look at our calculation before in the example, we had the real part as minus 1 over square root of 2. Square root of 2, which verifies the real part of our poles, and the imaginary part was 1 over square root of 2. So 1 over square root of 2, and that is also plus minus as a verified, that verifies our example as well. Okay, so that means the LQR function of Matlab actually gave us exactly the same results as our hand calculated example. Okay, so let us construct the state feedback closed loop system, and this is a state space system with the new system matrix A bar, but the remaining terms are the same. Okay, so this will give us our new system. Okay, and now let me simulate this system from its initial conditions. So I will have y t x is equal to initial condition simulation, sys closed loop, and the initial state x0, and a time duration, let's say 10 seconds. Okay. So now we have our simulation. Y is the output, which is our initial state. Okay, if I wanted to plot y, by the way, t is our time variable here. So I can plot the output versus time, and you can see that the output starts from 10, and with fairly quickly it converges to 0. So our regulator achieves what it's supposed to do, which is to take the state, the first state, from 10 to 0 in a fairly short amount of time. Now, we can actually also take a look at the individual states, because our command that we used actually also calculates all the states for that duration of time. So if I take a look at the X matrix, you can see that it's composed of two columns. The first column is the first state, and the second column is the second state. Okay, the second state is the velocity, remember. So I can also clear my plot. So close my plot, plot t, and let's say the first column, which is my first state. This will give me the same plot, exactly the same plot, but I can also plot the second state. Now you can see that the second state, which is the velocity, starts at 0, which is the initial state, then actually accelerates with the negative velocity, so that the first state approaches 0, and then it slows down, and then eventually the velocity goes to 0, so that the entire state vector converges to 0. We can also try to see what the input does. Okay, remember what is our input. The input is actually minus k times the state. But remember that our k, the feedback vector, is a two-element vector. But here x is somewhat not our state vector, but a time evolution of our state vector. So if I take the transpose of x, k will multiply every two entry of the state, so that I will get a u vector, okay, in time. So if I close my plot and plot t and u now, I will have my input versus time. So you see that the input starts at minus 10. Okay, so it starts with a fairly high negative force value, and then as I approach the 0 state, actually I slow down, or in fact the applied force actually becomes smaller, and then becomes negative and changes sign, and then eventually approaches 0 at steady state. Now it might be interesting to see what happens if I start suppressing somehow the input. Okay, so let us take this, where is our plot? Okay, so this is our plot of the input. Let's hold on to this plot, and now I will try to design a new LQR controller. So let's take a look at this. So I will change the R matrix. Okay, so let's see what happens in that case. Okay, let's say that R is not 1, but is 1.5. So that we have more penalty for the input in the cost function. So let us design our controller again, like this. Now we have a new system, so let's recalculate a bar. And let's design our system again. So we had sys closed loop 2. Okay, we had the first closed loop system. Now I'm designing second one. Okay, so this is going to be sys closed loop 2 ss a bar bcd. Okay, so that's our new system. Now I'm going to calculate a new initial condition simulation. So this is going to be, let's call this y2 t t2 x2, and this is our second system, closed loop system, but essentially the initial condition is the same and the time duration is the same, and here we go. Okay, now what do we expect? We expect that if we suppress the input more, that means the system will not be able to supply an as aggressive an input. So the input will be softer, so that the convergence of x to 0 will be smoother, slower, essentially. That's our expectation. And we also expect that the magnitude of the input will stay essentially smaller. Okay, here in our plot, we see that the magnitude of the input actually starts at -10. So let's see what happens in this case. Okay, let me calculate U2. We had calculated U as, so U2 will be equal to, we haven't changed, so K, so we need X2 here. Okay, so K is recalculated here. We have the second state vector. So this is our U2, and I want to plot this versus time. Okay, T2, in fact, which is the same as T1. So that's going to be, let's plot U2 on top with maybe another color. What was our initial color? Was blue, so I can use red instead on top. Hopefully that's gonna work. Okay, so you see the red curve now has smaller magnitude, but because we haven't changed R that much, the change was not drastic. Okay, let me repeat this with R is equal to maybe, so you see, so for example, if I wanted to have the input remain, now, okay, anyway, let's try to change, for example, this to R to 3. Okay, so we have R changed. Now recalculate our LQR, then recalculate our A bar, and what else? Okay, we have so sys closed loop 3, which is the new system with the recalculated A bar. Again, another initial condition simulation, and let's call this, okay, so this is 3 T3 X3 sys closed loop 3, same initial condition, same time duration. Okay, we have the calculation. U3 will be equal to minus K times X3 transpose. Okay, and I'm gonna plot again on the same curve. Now maybe we can use green. Okay. I'm not sure whether I was able to, did I? Hold on. Oh, sorry. Okay, so this was the same plot, sorry. I'm gonna plot T3, U3, and now with a green color. Okay. So you see that, and let me maximize this. So you see that as I increase R, clearly, I get smaller and smaller inputs. That means less aggressive actually less aggressive responses in each case. And let me show you, let's open up a new figure, let's say figure 2, and in this figure I'm going to plot all the different outputs, okay, and we will see how the output will slow down. Okay, so let's say plot T1 and Y1 with blue. Sorry, we don't have any T1, we have T. So sorry, what? Oh, we don't have T1, we don't have Y1. So TYB is, let me also put a grid on this. Okay, so this is our the first system's response in terms of the first state. Now let's hold on, keep this plot and plot on top. So I'm going to plot T2, Y2, and red was our color, I believe. So this is the second system, right? It has a slower response. You see that the time it takes to reach 0 is somewhat delayed. And finally, let's also plot the third system. And this with a green. Okay, and this is yet even slower. Okay, so that's our example, and please try to play around yourself with LQR and playing around with Q and R and different components of the weighting matrix, so that you have you can actually put an emphasis on different components of the state vector, as well as let me note that LQR is primarily used in order to design systems which actually have constraints on the input. If you have an actuator and you know that you should not exceed certain limits with your actuator, you cannot arbitrarily choose your pole locations. You need to be aware what's going to be the effort that will be exerted on the actuators. And so LQR optimizes that for you while trying to balance a good response in terms of the state vector, as well as having bounded or let's say desirably bounded control variables with respect to time. Okay, so that's going to be that is our example. Thank you and see you later.